Our next periodic trend is called ionization energy. Ionization energy is the energy required to remove an electron. And generally speaking, we're talking about removing the electron from the outermost shell. If I were to write an equation for what this looks like a chemical reaction for it, it would be as if I was going from F to forming F positive 1 by removing an electron from it. By definition, it's supposed to be in gaseous molecules, so sometimes you might see this. And some elements are harder to remove electrons from than others. And the reasons why are the same as the reasons why some atoms are bigger than others. It has to do with how hard the nucleus is pulling on the electrons. And so ionization energy is going to depend on two things. It's going to depend on effective nuclear charge, and it's going to depend on the number of shells. If something has a higher effective nuclear charge, then that's going to make it harder to remove an electron from. If something has more shells or more occupied energy levels, that's going to make it easier to remove, because the farther it is from the nucleus, the harder it is for the protons that are in the nucleus to pull on that electron. As the electron gets farther and farther away, the pull gets weaker. So if an electron is farther from the nucleus, it's easier to remove. If I were to outline my periodic trend for first ionization energy, that is the energy to remove the first electron, we find that ionization increases as we go up and to the right across the periodic table, meaning it is easiest to remove an electron here, which is referred to as a low ionization energy. It doesn't take a lot of energy to do it. And up here on this corner of the periodic table, we have a high ionization energy, meaning it's difficult to remove. If we ask you to make comparisons to which one has a higher or lower ionization energy, you can, generally speaking, just look at the position on the periodic table. So for example, I can ask you this question. Choose the one with higher ionization energy. Suppose I was asking you to pick between barium and beryllium. When I find barium and beryllium on the periodic table, they're both in the second column here. And when they're both in the second column, but barium's up here, I'm sorry, beryllium's up there and barium's down here, well, then since beryllium is closer to this position on the periodic table, it's going to have the higher ionization energy. Suppose I ask you to compare nitrogen and oxygen. Finding those two on the periodic table over here, they're in a row across where we've got carbon, nitrogen, oxygen, fluorine. And as I go this way across the row, ionization energy gets higher. So oxygen is going to be the answer. If you are asked to explain why, when you're asked to explain why, if they're in the same group, so remember the groups are the columns. When they're in the same group, the answer is based on the number of occupied shells. The one with fewer occupied energy levels or fewer shells has its valence electrons closer to the nucleus. The consequence of that is they're held more tightly. And the consequence of that is if they're held more tightly, it takes more energy to remove them, or they have a higher ionization energy. You may also be asked to explain them if they're in the same row. So if they're in the same row, then they have the same number of occupied shells. And the difference is due to effective nuclear charge. The one with a higher effective nuclear charge pulls harder on the valence electrons and makes them harder to remove, giving it a higher ionization energy.